Hello, everyone, and thank you for taking the time to join us today with another lecture in our series, Healthcare in AI and Healthcare. Today, we're gonna kind of go back a little bit to some basics, which is the core of whatever AI is, which is the core of data science, which AI was built on it, and that is statistics. And because we are talking about healthcare, we are going to talk about biostatistics. And we want something that is applied. So applied biostatistics for clinical reasoning is a very important tool that we need to keep to complement our skills in interpreting data coming from AI. So this is very important, and also it will help us understand the biases or the things that can throw off AI easily. Now, this is an important talk that I keep giving to my fellows, even outside the data science perspective, because clinical reasoning is something that we do regularly, and it's something that it should be kind of tethered into data in our head. So I always start with this joke. What is the difference between a data scientist and a statistician? And it's just kombucha, just like more hip, more new, something modern that came out of statistics. Like folks who used to do just boring jobs are now doing stuff that are interesting for Google, Amazon, all these type of companies, and now branching off to industry, to healthcare, to everything. So whatever you have data scientists, and it's kind of the new statistical applications in a sense. And our objective in this talk is to remove the glariness of huge numbers in our eyes. I always start this lecture by asking my fellows or the audience who thinks they're good with numbers. And maybe I'll see a hand or maybe I see zero. And the fact is, we are not built to be good with numbers. And when a number is presented to us, especially in a big context, it's always hard for us to gauge where this should be in our possibility or probability. So our goal is to try to improve our vision, maybe not to 20 over 20, but something closer to so we can actually see the numbers as they are. So I start with this. There is someone amongst you who have a nice startup, and they came with this spit test that diagnoses breast cancer. Okay. This test is amazing. It's going to be $1 billion company. It's 99% accurate, 99% sensitive, and 99% specific. Okay? I'm so excited. I take a spit and put it on, and it turned positive. What happens now? You are my doctor. What is the chance of me getting the disease? Should I be writing my will now and saying goodbye to my family, or should I just laugh about it and ignore it and move in my life? It's a very important question. It is something similar to what you see on a daily basis, maybe not as extreme, but you actually do see these day in and day out. So, the statistics deals with the collection, presentation, analysis, and interpretation of numerical data. Keep that in mind. Statistics is built on numerical data. How much of medicine or healthcare is numerical is something that we really struggle with, because you know what? Yes, your creatinine is a number. Yes, your blood pressure is a number, but it's not necessarily a numerical data in the sense that a creatinine of 2 is double or half of a creatinine of number 1. So the relationship between the number and the representation is not as straightforward. Hemoglobin of 14, hemoglobin of 7, yes, they're half of the quantity, but they are not necessarily a half anemia or full anemia or something. It's not that there's a linear relationship between the diagnosis or the significance of the number and the number itself. That's very important for us to keep in mind. In almost all healthcare data, we have more of a nominal or maybe ordinal category. Yes, no, I have nausea or no nausea. I might have some ordinal. So, oh, maybe the bloody nausea, the hematemesis is the worst. Maybe just kind of a clear biliary nausea is the least. You might create some sort of ordinal. Same for stroke, based on an NIH scale. You might have some other APGAR score, anything that has some ordinal data. And you rarely have, occasionally have what's quantitative, that's discrete or continuous as numbers. Eventually, all these are flipped into a decision that is binary. Yes, no. You have a disease, you don't have a disease. Yes, it's in this category or it's outside of this category. So this is very important that we eventually translate everything into a numerical value and then make a decision that is very black and white in its nature. And that's what's kind of classification or prediction, or whatever we actually use AI to generate output is trying to do. It's a yes, no. It's not, I don't know, or maybe. That's not what you're asking AI to do. We're actually asking them for a very clear yes and no. Okay. So it's basically biostatistics is the application of statistical methods in medical, biological, and public health related problems. It's a very, very important field, and we don't really have the proper training from the kind of a technical aspect of it. And that's why I'm trying to do this as a primer, as a kind of a start for you to talk about some of these problems. Okay. So variability in measurement is something that you always need to keep in mind as one source of bias. So I always start with throwing this off. Sometimes it's the observation, sometimes it's the instrument that you're using that's always kind of interfering with that value. And it always decision making is probability based, so numbers are very important for us for the probabilities. Okay, now we have some phrases or kind of concepts that we use, and sometimes we don't use them very judiciously. Like a lot of people conflate probability with possibility. So there's something that's easy, yes and no, impossible or certain. Am I alive or am I dead? Am I dead? It's either 0 or 1. There's not a chance or an even chance of me being something of that nature as of this moment. Okay, so it's very black and white, certain, impossible. There is now what is likely or unlikely, and this becomes a sense of the possibility. So in a dice, you have a 1 in 6 chance of getting a certain number, correct? So there's a 1 in 6 chance. So you translate that into a number. So it's roughly like 17%. When you talk about a likely thing, a 4 out of 5 chance of you pulling a blue ball out of this collection of four blue one and one red balls. So now you're saying it's probable that I'm gonna get a blue uh, 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 ball. It is possible I'm gonna get 1 out of 6. I'm gonna get number 1 out of this dice. So probability for 1 out of 6 is like 17%. Probability there is 80%. The probability conflates that there's a number that's attached to understand. Possibility just says it can happen. Can you see like a purple fly? Possible. How likely it is? Not very likely, right? It is possible within the realm of possibilities. The probability of that becomes a different story, and it's harder for you to quantify necessarily without having enough data about that. So always think of that as there's a possibility of a lot of stuff. The probability is what you're trying to create or use to make your decision. Now, even chance is a 50-50, like you're flipping a coin. Okay, so it's a 50-50 chance of you getting either head or tail. It does not have any other kind of a state, so it's a 50-50 chance. However, if you are repeating these experiments, it does not always tell you you're going to get 50-50. If you are flipping a coin 10 times, maybe half of the times you're going to get 50-50. Maybe another 10 to 15% of the time you're going to get 4 and 6, 6 and 4. It doesn't matter. Some less amount, maybe 10%, you might get 7 and 3. This is still within the realm of possibility. You know what? Statistically speaking, you can easily get 8 tails like randomly. Now, getting 9 tails in a row or 10 tails in a row becomes something that's possible. The probability of that becomes harder. And we're going to kind of learn more about how we can actually create this number for us to understand what we're dealing with and then make a decision. Because eventually, if you're telling me my chance of getting that breast cancer is 99%, I am doomed. If you tell me the chance is less than that significantly, say 1%, then I'm probably a bit more relieved. So that is where the probability becomes something that is very important for you to grasp and also translate into a decision easier. Okay, so sometimes this is something that's, oh, the statistical probability that you did is like 80%, and you said, okay, it's most likely, and it turned out not to be, or the opposite. If you're wrong once, that's fine. But if you keep getting it like wrong all the time, your statistical sense has some other things to do. Like some fine tuning is still needed for you to understand that, because you might be calculating it wrong or something else. Because let's say you're dealing with this rare disease, and you say most likely this is not this rare disease. You're right most of the time. There's going to be one black swan event that you actually might be wrong. And then you have to create a certain value in your head to say, when do I actually care to not be wrong about this? If it's a life-threatening thing, your barrier might be much lowered for you to do that. So you're going to invoke very expensive workup. If it's something that really has no significant health consequence and it's out of curiosity, you probably will ignore actually that. Okay, so we suck at numbers. This is no debate about it. And this is a nice graph that I'm showing you a line between 0 and 1 million. Okay, million is a number that we frequently deal with. Okay, uh, platelet counts, white count, money, so and so. This number is within the realm of measurabilities for us in a lot of stuff. Bacteria count. Okay, and now if I ask you, where would the 1,000 fall in this line? Your your head eventually puts it right in the middle automatically. And you say, no, 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 it's actually lower than that. And when I have student or resident or fellows in the room, they kept saying, okay, no, it's actually closer. No, it's closer. And maybe it's somewhere here. But in this line of a 0 to 1 million, let's say it's 1,000 pixels. You know what? The 0 and the 1,000 live in the same pixel. And it's hard for us to actually grasp this as like, oh, impossible. The 0 and 1,000, there's a huge difference, but not compared to 1 million. Keep that in mind. Like a millionaire will not care about an extra 1,000 more or less in their, well, they care, but it's not going to make a huge difference in how rich they are necessarily compared to someone with $100, right? It's all relative to that. So 1,000 to 1 million, it's not, like it's insignificant as is 0 to 1 million in a sense, at least in the scale of 1,000 grain. Okay. You probably heard of this story of the invention of chess, where this Mongol king was so impressed by this game, and he wanted to reward the philosopher who created it. And that philosopher was a very nice mathematician and said, okay, you know what? I want to make sure that my family is fed. We are in times of famine and feast, and I don't know where things gonna be. I just want some grains. And the story sometimes says wheat, sometimes it says rice. And he says, I'm going to start with 1 grain in the first square and keep multiplying it 2, 4, 8, so and so until you reach the square 64. And the king was furious, like, I'm the king of kings, I'm so rich, and you're asking me for a bag of rice. And said, no, 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 just please do the calculation. It's going to be a bit more of a bag. So, how much do you think at the end of this 64 iterations did he ask for? Now, I would love for you to actually guess in the chat. 1 million, 1 billion, 1 trillion grains? So I've got one answer for 10 million. Okay. 10 million grains. Is 1 billion too much? Is it in the realm of possibility? 1 billion. So the number of grains he would have accumulated by the end of the 64th square is 18 quintillion, which is 10 to the power of 18, and then 744 quadrillion. And so that even a trillion is now in the margin of error of this number. Imagine that. 64 iterations, 64 amplification times. That's all it took. And it's duplication. It's not like times nine in an R node for a COVID infection. Okay. So within 64 iterations, we reach a number of 18 quintillion. And for us, throughout the history, we have not yet grown that much grains, believe it or not, of any single type. And for you to get that much of grain, you need to dry the entire Earth's surface, harvest it continuously for 7 years, and then hand it to that guy. So, of course, his gift was not granted because it's impossible for it to be granted, and he had to settle down for less than a bag of grains that he asked for. So this gives you the power of like numbers and multiplication and our inability to imagine where things could quickly become. And this is a duplication graph. Okay. So now when I ask you what's a million to a billion, hopefully you've remembered the first lesson we talked about. And you know what? The zero, the thousand, and the million all occupy the same like pixel in this billion line. A million plus minus in a billion is one in a thousand. It's really insignificant. It's a margin of error. A million is a big number. And so is a billion. But for you to think zero, a thousand, and a million occupy the same like point in the line, it's hard for us, but remember that. Okay, billion to the trillion, the same. So now we're talking about a trillion being a margin of error of how much rice he wanted because it's like 6 digits or 5 digits down from what he actually was requesting. So our brain tries a trick in these bigger numbers, especially with using the decimal system, counting how many zeros and creating a relationship with how many zeros. So that's sort of a logarithmic scaling, right? So 10 in 100 is the power of 2, 10 to 1,000 is power of 3. So it's easier for us to imagine, okay, how much relationship between this number and that, and in a sense, but this is not a numerical, it's more of a logarithmic scale, okay? And we use these especially in things that really have exponential powers or exponential growth, such as bacteria growth, such as this rice example, and such as Richter measurement. So Richter is a measurement that they use to kind of quantify the earthquake frequency and destructive power. And in this, it tells you the difference between 2, 3, 3 to 4, 4 to 5. And I will tell you that the difference between 2 and 3 is 32 times. And so between 2 and 4 is a thousand-fold increase. Okay. And you can see here some of the events that actually shook history and what they were and the magnitude. And now, when you actually are talking about energy release, you have trillions of pounds of bomb explosives quantifying this amount of energy that is released from this earthquake. So when you talk about, oh, it was a 7.6 versus a 7.7, this decimal point that might not be that much to you, it's actually not 10% increase. It's not 50% increase. It's not 100% increase. It's a fold magnitudes of increase. This 0.1 point on the Richter scale carries multiplications of that, because I told you between 8 and 9 or 7 to 8, it's 32 folds. So this decimal point actually is living that logarithmic line there too. And it's actually going to depend on which it might have different values from like different decimal that you're talking about. Okay, so this, even with this, our brain is really struggling with this, like these huge numbers, and that's why it is important for us to understand that things like LLMs, like language models, AI, live on these huge numbers, and that we try to get a representation from that, and we understand how limited our ability to understand, but we are building the tools to know when things are off. And we have this intuition, and we're going to add to it something else that hopefully will help you. Okay. So culture versus PCR and upcoming diagnostics is a clear example. I'm not sure if you guys run some of these PCR tests that are quantitative. And it's really fascinating when you have someone who is like febrile and you have no diagnosis and these, and it gives you these weird bugs that you've never heard of with some kind of quantities, and you have no idea how to interpret. Or you check for this pneumonia and it has three organisms, and like one of them is horrible and resistant, and like I don't know which one I need to focus on. Oh, it's like there's one to the 10 to the power of 7, and the other is a 10 to the power of 4. And now hopefully I can give you like the sense that really the to the power of 4 is one of 1,000 of what that is in 10 to the power of 7. So the organism burden is much lower, that you probably have an infection from the one that is of the highest number and not necessarily the lowest. And now you can say, okay, I probably will focus more on the 10 to the power of 7 and ignore that to a sense, because the volume of it is not that huge to be the major playing factor. Okay. Now, averages is something that the machine lives on, okay? Every machine learning algorithm works on finding an average and representing that in a point, and then based on that, creating a kind of a classification intuition, okay? So it's all games of averages. It's average distance of a point between different dimensions, and that actually what gives it the predictive value. Everything is averages, okay? So when we think about averages and distribution, it always comes to our mind this graph that we all learned in medical school, and maybe we saw it later. It's this the Bill curve, with bilateral values that are symmetrical, and the standard deviation that we're showing here is like 34.1 and then 13.6. This is how we imagine the distribution of numbers. So we always think, oh, the value of the average gives us a very stable, centralized point. Okay, that is not the reality of life. So let's say we have a mix of students, fellows, and attendings on this call, and we say the average net worth on this call is somewhere in the magnitude of, let's say, 550,000 Canadian dollars. Okay. Now, none of us actually have that much exactly. Some of us had more, some of us had less, some of them had way less, but it's a representation of what the collective of this group averages. Okay. So it does not represent any of us, it represents the collective of all of us. Okay. Imagine by mistake Elon Musk dials in. What happens to the average of this call? The average net worth. We'll all be billionaires, despite none of us being a billionaire. You know what? It's not only this call, the building you are on and the building I am on, if they also put in that, we will be way, way, way much more rich, would be much richer by this person coming into this value. And this is an outlier that shifted the entire number. So this is why machine learning algorithms are very prone to biases by like outliers, and that's why there's always these tools to try to weed out the outliers or weigh them out, because they might throw things off significantly. So averages are not necessarily the best thing you can do, and understanding that and how one single value can actually throw the entire things off, and that value could be a mistake and it could be a real occurrence. Like how many Elon Musk are there in the world? There's only one. How many like 8-digit or 10-digit people like rich in this world? I mean, we're talking about maybe 100 or something. So, but this is out of 8 billion, 8 and change. So these actually are anomalies in the sense of the word, and they throw averages off significantly. Okay. So when you talk about distribution, there's one value that I try to also put in your head, which is how kurtotic this value, this curve is, meaning how much there's a variation between the center or the mean or the average and the rest of the population. So there's what they call mesokurtotic curve, meaning there's a kind of a balanced distribution, the Bill curve that we all see. There's elliptic curve, where things fall in a range that is not necessarily very far from the center. For example, average height for a male in the world, let's say it's 5 feet 6 inches or 170 centimeters. Okay, there are folks who are 195 centimeters, and there are folks who are 155 centimeters or 45 centimeters. They exist. There might be a person who is 100 centimeters. Okay. There's not a person who is 1 centimeter height. There is not one person that is 6 meters height. So it's kind of within a close range that you should expect the anomaly easily to come out. Like if you have someone who's 60 meters tall, you know this is probably an anomaly out completely. So you can put some sort of boundaries for you to get these values. Okay. And this is what they call platykortutic curve, which it's like an open space. You can have someone with $0, and you can have someone with $1 million. You can have someone with $1 billion. It's all over the place. The value can be anything in between. Okay. So the general population count typically are in the musical curve for income-wise. Physicians typically, if you're an attending physician, there's a specific range that you kind of dance around. Like you're not going to be hopefully making like 10,000 US dollars or Canadian dollars. You're not going to be making 10 million. We're going to be in the range of like hundreds of thousands, for example. Okay. And income-wise, like LPNs or ID physicians, it could be all over the place in a sense. As a joke, like some people actually are like very, very less fortunate compared to other specialties. So the second value that you need to keep in mind is the skewness. So the skewness is the difference between the mean, median, and mode. Okay, so in a sense, the left skew tells you there are more of the higher end of the value in this population than the lower end of the value. For examples, CEOs. In the US, CEOs typically rank a million plus income. Okay, so they're all in the million to 10 million to 50, 55 million. Like this is the range of their income. There are CEOs that decide to go and be a CEO of a nonprofit and get an $80,000 salary. They're the minority. Okay, so they're actually on the lower end of the curve. They exist, but they are like in the minority, not necessarily the majority. So here, the mean, when you actually average all these, is because there are some folks who are way down in the curve. They're going to pull the mean down a little bit. If you look at the median, it still kind of gets you a bit closer, and the mode is like the most commonly frequented number. Okay. Now, the normal distribution, all three values are on the same spot, which is really not that common in real life, in real scenarios. Okay. Now, the right skewness is the opposite, where you have a minority of folks on the higher end of the spectrum, and the vast majority are on the low. So there is one Taylor Swift in this world that it's a billionaire. There might be 5 or 10 billionaire artists in this world. And there are hundreds of millions probably of artists who are waiting tables or like doing Uber or other jobs for them to follow their dream and also make a living, because art is not making them a living. They're living really, really in a modest way. So when you actually take a mean, because of one Taylor Swift, it's way skewed to the right. The mean, like it's always in the right, but the skewness actually is the left, and the skewness is towards the right, and it gives us the impression that, oh yeah, you're an artist, you must be rich. It's the opposite, my friend. Artists are usually you're not gonna be wrong if you're saying 10 out of 9 out of 10, they're gonna be on the poorer end of the society than on the richer side. So fame does not necessarily also equate to richness. So keep that in mind, that we are skewed in our attention just because you have a few values, but the reality of it is artists don't make that much money. Okay. So now you understand the kurtosis, which is how much the variation between the average and the values around it, and the skewness, how skewed was the left or the right, which ones actually have more of the values than the other side. It's the higher end or the lower end. Okay, so this is a nice example to start applying some probabilities, because eventually everything again is a probability. Everything is moved to a probability calculation. Raul, his favorite breakfast is bagel. Favorite lunch is pizza. Okay. The probability of him having a bagel for breakfast is 3 out of 5 times. Okay, so it's 0.6. And having pizza for lunch is half of his time. Like half of his days are going to get pizza. So it's 0.5. What is the average of him, if it's completely random, to have both on the same day? It is very easy when these are kind of completely independent and you say, oh, it's not because of his mood or his financial, is you multiply the probabilities. So 0 0.6 multiplied by 0 0.5, it's 0.3 chance of him getting both the same day. So one third of his days is going to be having his favorite food. Okay. Less than both, but it's still a good chunk of his time. And now you actually have a kind of a number that is easily to be calculated. Now we know if you're meeting Raul, 1 out of 3 days is going to be having both for his meals. Now going back to my test, let's try to apply probabilities. Okay, so it's a breast cancer spit test, 99% accurate. I took it and it's positive, and I'm coming to you to interpret this test. Who would like to give it a chance and tell me what is my calculated risk of having the breast cancer? Let's open the chat and see if anyone is adventurous to throw in a number. Oh, Dr. Khurshid Muhammad. Yes, absolutely. Absolutely. So he said it will depend on the baseline incidence of breast cancer. So you need to look at what we used to uh, kind of parrot. Oh, the pretest probability, the pretest probability. What is that basically? It's like how often does this happen? Okay, so breast cancer is on the top three because of cancer worldwide. Some places it's number one. Okay, for female. But what about males? So, roughly speaking, the annual incidence is 1 in a million. Okay. So now the baseline incidence is really gonna change how you interpret this value of a test. Let's see how together. Okay. Now, if you will pop asking me what's my chance of having uterine cancer, it is, I hope, 0% because as an XY with no other weird internal organs, I should not have a uterus, so my chance of uterine cancer is zero because I did not fulfill the prerequisite, which is having a uterus. But I do have breast. I do have male tissue for breast. Okay. So my uterine cancer chances, I can say impossible, but it's not for it's not impossible for. So now you are meeting two conditions. I should have a disease and I should have a positive test. Okay, for me to interpret this, or at least I need to kind of create a volume for both circles to understand what the chance of them actually uh, uh, intersecting. Okay, so let's say this is a table of the entire population of 1 million people. Let's say these pixels are all like individuals, okay? And let's say I am screening the entire 1 million people with this amazingly accurate test. How many will be falsely identified? It's 1% of the million, which is 10,000. So they're going to be 10,000 people who are positive uh, for this test, okay? And there is one person in this entire million who actually had the disease. So a positive test puts you in one of these two categories. Either on these unlucky folks out of the 10,000 who are going to be ruined for their day by this like, bad news, or that one unlucky person, or maybe lucky because he was diagnosed like haphazardly, randomly of the disease. So you can only exist out of one of these. Okay. So basically, your chance of you having that disease, if you look at this kind of purple line, these are all the folks who screened positive. And there's one dot on the corner, it's one single dot that have a lot of redness around it in another circle, just to show it how where it is, because you cannot see it. That is the actual patient that's going to be picked up by this 1 million tests. Okay. So the chance basically becomes 1 divided by the one true positive plus the 10,000 false positives. So it's 1 over 100 and 10,001 and it's 0.00009%. Now we have a probability of what actually this test means based on its sensitivity, specificity, and based on and taking into consideration the annual incidence of this disease, which is really, really low, okay? Compared to other diseases, of course. So now you are kind of equipped to understand this table in what values that actually represent and how to actually interpret sensitivity, specificity in the setting of less often occurring diseases, like rare diseases or rare events. And also, we're going to try to apply it now in an applied way for a bit more of a common conditions that we as internal medicine folks, and I'm sorry, all my examples are from my clinical experience. I have not done neonatology in my life, so I'm sure you can relate to them, some of these based on the populations that you see, but let's take this clinical example. So we have a 76-year-old male patient who is known to have diabetes, kidney disease, and some heart failure coming to you with shortness of breath, dyspnea, basal crackles, lower extremity edema. Now we have PAs and our EDs, and they initiate this dyspnea order set. So it's a one size fits all. It says everything. CTA of the chest, looking for PE. It has the D-dimer. It has blood cultures. It has sputum cultures. It has troponins for enzymes for the heart. It has EKGs. Everything is being sent. Okay. So the D-dimer, which is a test that was part of this panel, comes elevated at 1187. Okay. There's an ED physician, ED resident who is excited about using his ultrasound skills because ultrasound is everywhere, as you can guys tell. And we have an expert who's doing it for the brain. I really enjoy it. Khurshid's images of like this brain ultrasound images, like amazing. And this person says, okay, I'm going to look at the heart and I'm going to look for any RV strain. And he does, and there is RV strain. So now he's more concerned for VTE or venous thromboembolic disease, which is the PE we're talking about. So now we are trying to establish a diagnosis in someone where two surrogates of a disease are present. So let's say there is a number of chance of this person having PE, which is the less likely diagnosis from the clinical symptoms, but is suggested by the D-dimer elevation. And does this new RV strain increase or decrease the probability or the clinical judgment about this disease? And this is an important factor that you need to keep in mind, that these are both are surrogates of the disease and not necessarily are the identifiers of the disease. And clinically, almost everyone will think, oh, now that they actually have also RV strain, the possibility of them having PE must naturally go up. And the fact actually it should not change because both are surrogates, both actually can occur in this disease, in other diseases. So the fact that they are both here today does not change the fact that this is a person with heart failure coming with classical symptoms of heart failure, and there's no need for us to invoke additional tests. Unfortunately, almost every patient who comes to that emergency room will get a CT angio of the chest looking for PE to rule it out, and it's going to be negative, and like the vast majority of these, or might actually find something incidental that is not related to the clinical presentation that he had. Okay. And this is what we try to create. We always try to quote this correlation line in our head, which we don't understand. So the more the scattered the values, the harder for you to come up with a line that is meaningful. So D-dimer is all over the place. The only value we have in it clinically, when it's negative or low, it has a negative predictive value. So there's really low chance of you having a PE when that test is negative. But if it's high, really does not make much sense to us, and you have to go back to the clinical findings. So it's a test that throws off and does not really help that much. Okay, so there is a correlation between the D-dimer and RV pressure on echo, but that does not necessarily translate that if both are up, that the third dimension, which is the PE probability, necessarily go up with them the same way. While they actually have a positive correlation in this, it does not translate that they actually have a positive correlation that is in the same magnitude or the similar direction for the third factor that is shared between them, which is the PE, which is, let's say this is X and Y and the Z is the PE. It does not correlate to that. Keep that in mind, that there might be correlations between two, but the third might not completely be isolated from that. Okay, so this is another kind of exercise to talk about how we interpret like events. So a person's birthday, of course, is only 366 possibilities. I mean, if you count, if you exclude February 29th, it's 365, which is the year length, unless it's every fourth year. Okay, so the chance of you not having your birthday today is, statistically speaking, 364 out of 365 days. If it's your birthday today, happy birthday, but almost all of us are not going to be their birthday. So the chance of me not having my birthday today is 99.726%. Okay, that's the chance of me not having my birthday today. The no way chance is then 99.726, the rest of the numbers. So now let's talk about, okay, on Eid party, the residency program throws a 23 invitee and a room for some Turkish food. While knowing each other, what is the chance of 2 out of these 23 having the same birthday? And some people automatically say, oh, it's going to be even less likely because the no way is already 99.62 something, whatever it is. It's minuscule compared to the 99. And I'm going to multiply it by 2, so it's going to be even a lower number of it's not being someone's birthday. However, there is an interesting phenomena here that we need to kind of talk about, because this is now, we're talking about 23 attendees. And you are trying to create a pair that has the same birthday, right? It does not matter if it's today or not. So this is actually a very different game that we are playing here, okay? How many pairs can you make out of these 23 attendees? Easy. It's 23 divided by 20, multiplied by 22 divided by 2. So there are 253 ways of potential pairing between these 23 attendees, believe it or not, okay? Now, we're talking about, okay, now I'm going to multiply the no way by itself 253 times, because I have run this experiment 253 times for me to see if there's a no way the chance of me getting my birthday. And believe it or not, now the chance is 50% almost. So if you have 22 to 23 people in the same room, you have a 50% chance of 2 of them having the same birth date. Like, June 22nd, for example, or like July, whatever. It does not matter. It's not the day. It's some day in the random 365 days of the year, both actually share. So this is how you also have to kind of understand that the pairing and the way you actually calculate it is different from like just kind of trying to multiply it twice. You are multiplying it by itself 253 times, because this is how many pairs you can create out of this set. And of course, this is called the birthday paradox. And if you graph it, if you have a 70 or more people, you're going to have almost 100% of a chance of 2 people actually having the same birth date among the attendees. So in any wedding that is like typically like our Arab or Desi weddings, we have 100 plus almost all the time. So it's always going to be 2 people having the same birth date. Okay. What's the chance of him having the birthday today? Now you tell me how you can calculate that, and what's the chance of that? Which of course is going to be really, really high, because now you're adding a third dimension. Not only they're going to share the same birthday, but it's have to be today, which is now a different talk than the other one. Okay. Let's run another clinical case. And this is a common thing that we encounter in our healthcare sector. It's always a good example that I bring to the audience. We have an 86-year-old female who comes with left hemiparesis. The CT of the head shows a very unfortunate right MCA infarct. And for some reason, the ED sends UA, urine analysis, and comes with bacteria. And now the urine culture is growing VRE. and they are deciding whether to treat or not. And I'm trying to convince them maybe there's something they need to keep in mind. Okay. So, how can I calculate what the chance is for this to be a true UTI? We will grab the baseline incidence. It's 5% of UTI per annum. Okay. So per day, the chance of a UTI randomly being picked up in that person is 0.5, or the 5%, divided by 365 days. So it's 0.000137. Not that huge, okay? So what is the probability of an asymptomatic bacteriuria in a 68-year-old individual? Is 50%, meaning 1 out of 2 elderly, if you culture the urine today, is going to grow something, and they're going to be completely asymptomatic, have no infection. So 50%. Okay. Now, if you are trying to randomly pick an actual UTI in someone who's not coming with the symptoms of a UTI, right? This is completely random now. It's not like you're screening for UTI randomly, okay, in this event. So the chance of them to get, for you to get a rounded number, we're going to use the million number example. So in a million, we're going to have 137 cases of actual UTI. If we bring a million elderly folks and screen them, randomly, we're going to diagnose 137 out of them with real UTIs. But we're also going to screen 500,000 of them for positive urine without having a UTI. So then the chance of them having this test positive and having a UTI is the true positive, 137, divided by the true positive and the false positive. And the magnitude is going to be 0.000274. Okay? Now, this means that you need to treat 3,650 cases to actually encounter one true UTI using this method. You are not going to see 3,650 encounters similar to this in your entire career if you're an internal medicine ED physician or an ID physician or whatever physician. Okay? So the chance of you encountering this in your real practice is almost non-existent, that you actually are picking it up randomly. Okay? So that tells you in a sense that it is impossible for this to be picked up randomly by this test in this population. Therefore, you can easily say, I will never treat a positive UA in a stroke patient who's not having any symptoms and be 100% safe in your career, or 99.999 something, whatever, okay? Now, if you are giving ceftriaxone, which is the empiric regimen for this, having C. diff with the ceftriaxone is 1 in 1,000-day treatment. Okay, so and for you to treat that one case, you would have cost 142. Sorry, for you to get 140 to treat one case, you're gonna actually treat 3,650. You would have caused 142 cases of C. diff doing that. Okay, so you've actually caused 226 cases of C. diff for you to try to treat this. So this is why now, adding probability to your clinical sense that is based on numbers that you now hopefully know how to calculate from your extensive knowledge as a clinician, and also using ChatGPT thrown in numbers, you are now able to translate these into things that you can look at, to numbers that you can interpret and say, yes, possible, but is it probable? And this is the most important part of what you are trying to get out of any classification, prognostication, or suggestion tool. Is what they are actually throwing at me possible or probable? Because again, they're not throwing into gospel into you. They're throwing a suggest or a value that is based on a calculation that we spoke about. It is very complex. It is very multidimensional, and these multidimensional things, you're going to have one value or a couple of values that are completely out that might throw things off. And when you understand how one value can throw things off, and understand that you can incorporate your clinical sense, your hinge, even, like, you now have a better way of coming up with a way to deal with the things that the AI model gonna throw at you. Remember in the first lecture when we talked about that amazing skin cancer model that was trained on amazing data and exceeded the three top world experts, and then diagnosed skin cancer in a bed sheet that has Mickey Mouse embroidered on it. Again, this is a mistake that you will never do because you know better and you can recognize Mickey Mouse logo very easily. That's not something the machine necessarily can do that well. So these are the tools that you can keep in mind in your. I'm going to skip this example. So I'm gonna skip these because I'm trying to get to the point of us more focused on how we understand the role of large numbers, and large is the word that is in large language models. The large, the big data is nothing but large data sets with large values. Okay, and we are probably equipped to deal with numbers up to maybe 70 something or 100, no more than that, and we can handle maybe 7 digits together, and that's why we have 7 digits in the phone call number, the phone numbers. This is how like easy for us as an average person to deal with how many numbers in the consequence we can actually learn. So understanding that now you know why it's very hard to deal with large numbers, and then why it's important for us to understand how to bring probability into the visibility of our decision, because now that's going to be the factor that tells you what you're dealing with is a real black swan event or a real outlier that is completely nonsense, or how I can interpret this. Because we are going to be on the verge of hundreds, maybe actually thousands of decisions made by AI that's going to come to us, and we can have to sit down and try to make sense of it. And from your clinical practice, I'm sure a lot of you are ICU physicians, okay? And at an average, each ICU physician is dealing with 2,000 data points every morning from the vitals that they've calculated, from the lab work, from so and so. But you don't incorporate all the 2,000. You probably use maybe 10, 20 data points that you actually use to make your clinical decision on your patients. But keep in mind that this is the actual world, and these 2,000 data points, we are missing stuff, absolutely. And there are going to be noises that actually going to maybe point us into a very wrong direction. And now we navigate the world with hopefully a little bit more of certainty and a little bit of a clinical statistical hint, kind of a hinge. And thank you, everyone. And now let's open some questions.